Thank you. It was. I'm going to say some things that may be provocative or naive. I don't know, but I was pretty nervous about it. But now I feel better. I feel like it's okay. I won't be sticking out too much. And there is sort of a question if you're coming from a real math background. What can you contribute? And I think there are things, and this is sort of an unusual talk, not the type I give terribly frequently give. I'm really not going to talk about what I've done. I'm going to talk about what I hope to do at IPAM. What do I think are the interesting questions, and where do I think maybe a mathematician could contribute? And this is my personal view, and if you disagree, I respect your right to disagree, which is now very well established. Okay. And I do feel bad. There was one time you came up to me and you said, I disagree with your model, Keith. But now I kind of was like, but now I have a much better context. It's not such an unusual thing for you. I feel like I've sampled better. Okay, so what I'm going to try and lay out is how, from a mathematical point of view, you might think about correlation in mathematical models. A little bit of what I'm going to talk about comes from a grant that Michael Morello forced us all into writing on turbulence, and sort of ideas from there. So it's a little bit of a turbulence approach. And I apologize, if you've been at the tutorials, you're going to see some of the slides are the same, but then I'll diverge. And so I'm going to focus on water, and understanding the structure of water, and from a mathematical point of view, I guess I'd like to try and say that the structure of water is a problem that is similar in spirit to the idea of turbulence, which is also kind of a water problem, but on a very different length scale. So this is just, from a mathematical point of view, wandering through the computational quantum and molecular literature. It's a little bit like, a little bit too much. And so the papers I've settled on, I'm not going to say these are the definitive papers, but these are the ones that caught my eye and that I could make some sense out of. And so one of the things that I really liked about this one is, because this is exactly what I would do. I would take water and I would try and break it. They took a relatively large block of water in a molecular sort of simulation, and they sheared it tremendously. If you're a mathematician, 0.16 nanometers per picosecond is an odd set of units, but it's like 300 and some miles an hour. So it's not too far from the RMS velocity of the, so they're shearing this block. And they want to understand, what does this do to the structure of the bonds inside of water? If you're also a mathematician, haven't thought about water very much. It's highly polar. It's certainly not a sphere. All right, water, that's a very important feature of water. It's really a dipole, strong dipole moment. And what you see, and what I think many people know in this room, is that it forms, and I got to use this sort of weird mousy thing here. It forms networks. And it does this, it forms them and breaks them. And in fact, all of the hydrogen bonds, which are these sort of colored things inside here, are sort of done post-process, because they're just looking at distance and angle of orientation between the waters and saying, okay, this distance, this angle means they're forming a hydrogen bond. And that's kind of an interesting idea for me, that that's something you can do. And so what are they tracking? Well, one of the things they're really tracking is the distribution of hydrogen bonds in water for different temperatures, but really sheared and unsheared. So under this tremendous shear, what to me seems like a very tremendous shear, the sort of shear an airplane might put on water. You see this distribution, what did Axel say, 3.5 water molecules, so that's the average, but there's a lot of waters that have 4 hydrogen bonds, 3, some with 5, some with 2, and some with 1. A non-trivial amount have 1 hydrogen bond, and that means it's in a fairly high energetic state. And when you shear it tremendously, some impact, but not that remarkable, not tremendous. You sort of lose a little bit of the high correlation numbers, the ones with high hydrogen bonds. But it's a fairly robust structure. And so this formation of this hydrogen bond network, I think, is formation and breaking and rearrangement, I think, is a fundamental property of water. I don't think it's a strong statement. And it leads to sort of, it sort of correlates with many of the anomalous properties of water. That this is really a relatively large energy distribution in the water molecules. And so this long tail of the energy distribution in water really is, I think, an important feature of it. And so I won't go through, but I think the ones everyone's most familiar with is the density maximum is at 4 degrees C. So when you freeze it, salt ice floats, partly because of this interesting sort of structural correlations that happen inside of water. If you haven't seen them, this is sort of a classification of the water clusters. There's, 8 that are seen as sort of the predominantly lowest energy, and there's at least for some period of time, a debate about which one actually has the lowest energy and by how much. But what I would say is that water is doing these. In some sense, I view these as the Maxwellian structures of water. This is what water forms. All right, this is the low energy guy. Okay, they already knows. Good. Okay, that's good. From a mathematician's point of view, I would hesitate you to jump in. I'm talking to the mathematicians right now. But if you say something is unequivocally, unsustainably wrong, please do stop me. Okay, so I would say that these are some of the structures that form, and how long do they last, and how do they pack together is sort of an interesting question. But the idea is that there are fundamental structures. And one of the features about water that I think makes it interesting is that these long tails are something that is, in some sense, your own biology is using in a very strong way. This is a simulation from Greg Voth. There was an earlier one I saw from Gerhard Hummert that really sort of opened my eyes a lot. So bulk water, and then connecting 2 regions of sort of bulk water with a very narrow cylinder of graphene, so very hydrophobic material. And so the water really cannot bind strongly with the graphene. And so they tend to go in single file. And so these water molecules are sort of reduced to having at most 2 hydrogen bonds. And if you have 3 or 4, that's not very, very likely. But if you only have 1, then that's actually an increase. It's some benefit. So they're really, what this is doing is harvesting the sort of low correlation number water molecules and getting them to form this water wire, which can then conduct a proton very effectively. The proton diffusivity goes up by orders of magnitude when you have this water wire. And in some sense, this is sort of the sort of mechanism that your proton channels use inside all of your cells. So in some sense, this is hardwired into your DNA, literally. This is how the proton channels are being conducted, is harvesting these high energy molecules to form water wires and then use them to conduct. And so this is really one of the key, I think, features of water that makes it quite interesting. Okay, so to get to sort of edge towards a sort of mathematical sort of ideas, like how would you begin to understand and compute some of the structure? There's a paper, Pruitt et al. In 2016, that I liked. I don't know if it's a great paper. It's been demonstrated, I'm quoting, that 3 body effects play an integral role in systems dominated by quantum many-body effects, in particular in water clusters. And so one of the things I'd like to understand is if I'm going to write down a sort of molecular model for water that I then want to coarse grain through BBGKY and mean field limits, what sort of properties should it have? And the idea that 3 body interactions are somehow fundamental is, okay, that's a good idea to get clear at the beginning if that's what you have to do. Because the coarse graining for 2 body interactions and 3 body interactions is quite fundamental differences. So this is 2 simulations. They did 2 body interactions, and they are resolving some sort of quantum, some sort of DFT sort of structure in here. I can't say I understand all the details on the paper, but their main point is they have something they consider to be relatively ground truth. They have the 3 body interactions are these dots. The 2 body are these sort of asterisks. They deviate by quite a bit. These are Hartrees. I had to look it up. It seems to be 27 Hartrees to an electron volt. So that's about an electron volt of evolution. They're taking a water ring configuration and allowing it to evolve. over, I don't know, 40 femtoseconds, and they see a change in energy of the structure of on the order of an electron volt, which is a lot if you're doing electrochemistry. And if you do the two-body, it really goes the wrong way. And moreover, they then call failure because they start to get too close to each other and they exchange protons and do other things that are considered to be non-physical. And so they really were not very happy with the results from the two-body sort of simulation. And they felt that really three-body is somehow essential to getting the structure of water right. And so I would say one of the things that really hit me in the tutorial, Jorg showed a picture, and he allowed me to rewrite it, and you can see the level of technological sophistication I have. I could not figure out how to embed the simulation into my PowerPoint, so I'm just going to open it up, and hopefully it will run. OK, so I can't say that I can answer any question, all the questions about this, or maybe even any, but basically you have what looks like an electrode. You have some semi-absorbed or some type of water, and then you're a safe distance away from the electrode, and you have bulk-like water. And I believe this is a huge simulation. It's a sort of simulation you wouldn't do very often because it is so expensive. But the question that Jorg was trying to answer in this group was, what sort of structure will you find in the electrostatic potential? I'm going to use two words. I'm not going to say electrostatic potential, particularly in the bulk region. And the conclusion that I drew, and maybe that's the one that I hope that Jorg wanted me to draw, was that it's large. It has a lot of spatial dynamics to it. It's got a lot of temporal dynamics to it. And in my head, and please correct me if you think I'm wrong here, I'm thinking of this as water forming sort of structures that are electrostatically favorable, but have probably bad geometric packing. And that these then have to be the geometric sort of entropic effects force it out and in, and it's like Sisyphus pushing some big boulder up an electrostatic hill only to roll back down because of the physical constraints, and endlessly doing this. And I would call this the song of water. That this feature, if you're doing electrochemistry, is probably actually a very interesting feature to have these large temporal variations in the voltage. If you go high and low, it allows you to achieve energies in the near field that maybe you wouldn't get otherwise. That maybe this is part of what makes water such an interesting solvent. That these large swings, that this sort of song of water that you better get right. The next time you drink a glass of water, try and listen and see if it's singing the right song. This is an interesting question. And of course, you would like to be able to push this all the way back. You don't want to have to simulate this for very long times. When people say initial data, a lot of what they're talking about is, well, how do I initialize maybe my explicit water if I have a lot of it? Because you don't have enough time to let it relax back down to this state. This is a very, very intensive thing to do. And if you start with the unusual or a high energy water configuration or a high energy configuration further, you're kind of stuck with it on the time scales you can typically resolve with these sort of ab initio simulations. So you'd like to be able to understand what is wrong. And to me, this is very similar at a very high level to the question of turbulence. What is the structure of turbulence? What is the structure of the spatial and temporal variation of density and dipole? Because water is a strong dipole, you're going to get these electrostat. What is that? What sort of mathematical model would I need in order to capture that effect? And so the rest of my talk is my somewhat, I don't know how to describe it, naive approach to build a model that might give a reasonable approximation to the song of water. Okay, that's my goal. Let's see if I can do this. No, view. Okay, so I'm going to just roughly give you an idea of a sort of, I don't know what you might call it, a Reynolds stress sort of approximation. This is, in some sense, largely borrowed from this experience I had working with Michael Murillo in this turbulence grant, which may or may not get funded. We'll find soon. So let's just look at a very polar molecule, throw it in, and ask what happens if I don't believe it has a mean, if I don't believe my molecular model, my sort of Hamiltonian ODE on n molecules, I think it doesn't probably have a mean field limit. It probably still has correlation. How would I then extract these correlations and preserve them in a mean field limit to get a continuum model? How would I put this sort of fluctuations in water back into a mean field model? And what is the approach to do that? So very sort of naive, I think this is called a Stockmeyer model. I'm just going to replace all this structure, and I'm going to do it in 2 space dimensions just because I just want to simplify things. Just replace this with a dipole. So I've got a charge, a positive, a negative, equal positive. Right? This has really got one negative and 2 positive charges. I'm going to completely simplify it. But putting that sort of data in isn't hard. What's going to be hard is to understand the correlations and get information on the correlations. OK, so I've got locations of molecules. I've got an angle, which is really your dihedral angle, but I'm just going to take it in 1D as spins. I've got a charge density. And I'm going to put this in and ask, what sort of continuum models would you like to get? OK, one of the dominant, as has been said several times, one of the dominant sort of parts of potential is Poisson's equations, electrostatic. And because these water molecules are in a vacuum, they are forming their own solvent. The dielectric is free space. That's pretty clear. I've got a Green's function for Laplacian. I should view this on a periodic domain. So I've got a Green's function on a periodic domain. And if I think of the 2 parts of this dipole, it's very natural, at least at reasonable length scales, to approximate it with just a gradient. Right? This dipole at 2 points is really just a gradient of the Green's function. And then you can write out an expression for electric potential, the interaction of this term with this dielectric charge gives me a sort of a local electric potential. This is sort of what was fluctuating in the previous screen. I can add them all up and get an electric sort of electric potential energy. If I knew all of the microscopic variables, and again, I'm doing molecular. I don't have any orbitals in here. This is all molecular model. If I knew all the angles, I knew all the positions, then I could say, here's the electric potential of my water. And what I'm starting with here, and this is one of the key points, this is all pairwise interaction. And that's a fundamental question for me. Would pairwise interaction have hope of capturing this sort of structure of water, this sort of song? OK, and just a notational point, grad squared for me is Hessian, not Laplacian. I'm a mathematician. OK, and Rij are the differences, the difference vectors. And so I should make a caveat. Of course, short-range forces are more complicated than this if the 2 molecules get close together. And you should do something more intelligent at a short range. Put in a short-range term, has some sort of angle between them, some sort of distance, some sort of like Maxwellian type collision operator, if you will, and add in a short-range term as well. If you were actually trying to simulate this, I wouldn't recommend simulating this without a short-range term. OK, but you can put them together and you make a Hamiltonian. Right? I have a 2-particle interaction and a 2-body interaction, kinetic energy. And one of the first things that comes out if you're interested in a mean field limit is that really you have 2 sorts of time scales that is immediately forced on you. You have a kinetic time scale. You have mass, which relates. I should probably get that out of the way. Can I do this? Nope. You've got mass, which relates momentum to linear velocity, linear momentum, and you have angular. You got your angular inertia I, which has a completely different scale. And it's got L squared in it. So much, much, much faster. So you're going to have 2 time scales. You're going to do a classic mean field analysis. It's already interesting. How would you scale this? In some sense, this model is very comparable to the one that Alexei Konyshev is going to speak, I think, later. So I don't know if he speaks about this, but he's going to talk about related things. So there are sort of very interesting, like non-local dielectric response of water nano-confinement. I like that paper, too, if you want to go. OK, and of course, then D, average of D, and we're going to see, well, capital D is going to relate to M, the polarization field that he uses. OK, so if you just want to write this out as an n-particle ODE, you got positions and angles responding to the linear and angular velocity. And now you have sort of 2-particle interaction, basically Newton's law. There are these very local short-range terms. I'm going to drop them now because I just want to look at the structure that comes out of this guy. And I think I have, no, I got M here and I here. These have very different sizes. So one of these is a fast system and one is a slow system. And I'm just going to call these right-hand sides, after I drop the red terms, fx and f theta. These are the sort of explicit potentials that are giving me my evolution of my system. Okay. Okay. So if you go through a BBGKY hierarchy, if you haven't seen it, okay, I'm not going to explain it. Tried to explain it in the tutorial. I don't know if I succeeded. But basically, you take moments. You look at an n-body interaction. There's no loss of information. I just say I have n particles. What is the probability of finding them at these coordinates? And then I take marginals of these, integrate out things I don't care about. And I basically get down, if I integrate enough, I get down to a one marginal, which is just the probability of putting one particle at this configuration independent of where all the other ones are. I'm just going to put it down, average all those out. And if I get an evolution equation for this, I get a sort of hyperbolic system. And I get coupling. The one marginal, of course, couples to the two marginal. This is explicitly because I have assumed two-body interaction. And you have some sort of kind of a convolution-y sort of thing. I'm going to call it a two-point convolution. I really want to emphasize the structure of this because it's implicit in the two-body interaction. If you have three-body interaction, you will get a different operator there. But you're just sort of integrating out. You're sort of taking a marginal here and then integrating over a couple of different variables. So it's like kind of like a generalization of a convolution if you haven't seen it before. If you go to the mean field limit, if you can prove it or if you believe it, then these k-marginals converge to k-tensor products of something. This is an incredibly nonlinear map. Right? Taking a function and taking k-tensors of it is very nonlinear. Right? If f is big, its k-tensor is huge. Right? So if you want this to be stable, it's incredibly sensitive to what f is, taking high tensor products. You really, this I think is part of the reason why the BBGKY is hard to approximate. This is such a nonlinear map. And all the nonlinear system comes, in the mean field limit, comes from this substitution of the k-marginal with a k-tensor product. That is what is really a hugely k polynomial, but you have all the k's. It's like an exponential almost, right? So if you do that, then these become, these sort of convolutions become, well, okay, in this case, I'm assuming a convolution structure for my force field. It becomes two convolutions composed. That's the sort of familiar sort of Vlasov system you would get. Okay, but I would like to say, okay, first of all, oh, no, don't touch that button. Gotta try this one. No, gotta come over here and touch this guy. Okay, this is no respect. Okay, now it's even worse. Okay, this is making this is like my dog. It won't listen to me. Okay, how do I get back? Where was I? Where'd it go? Oh, I'm on the wrong screen probably. I think that's what happened. Okay, how do I get to the right screen? Let's see, let's think for a second. How do you, there's ways to get to the right screen. Let's see. I think if I click on my talk, where's my talk? Yep, that's it. I just got to think of the right name. Okay, if I click on this, there you go, thank you. And okay, but I don't even know what button I touched. Okay, so this is the mean field limit. If you average it, I just want to just make sure people can roughly follow. If I average out the microscopic quantities, velocity, angle, and angular velocity, then you can get densities, local velocity, a density-weighted displacement field, and a density-weighted angular velocity. These are now I call these macroscopic quantities that people would like to sort of get a continuum model for. This is sort of where they are coming from broadly, one way to point. So basically, I project, right? I project my Vlasov system onto four explicit vectors. I take moments, and you get a system. And if I could get this guy out of the way, there he is. You get what is sort of a familiar, sort of roughly familiar-looking system, sort of Eulerian terms, what you might call well, these sometimes they're called source terms over here, but this can all be written in a hyperbolic framework. And you get evolution equations for these, and you might want to take them. Again, this one is much faster than this one. You might want to take some of them at equilibrium and say, what are the equilibrium structures? And now the sort of relationship between the displacement field and electric field, that's going to induce an effect of dielectric. That's sort of a lot of the structures coming out here. just in case you're paying attention, BOT is rotation by 90 degrees. And there's sort of pressure terms that you don't know. In order to get a closure, you would like to understand what these are. Well, these are the residual parts of this thing, this probably distribution that you need to understand in order to close this. But I think from our context, it's safe to say that these you can neglect. Taking these to be 0 is probably not an egregious approximation. Okay, but I don't think that's going to be very accurate because I'm not really sure there is a strong mean field limit particularly for water, for these dipole molecules. What you'd like to understand is the difference between the two-particle structure and the tensor product of the one marginal, so the two marginal and the one marginal. Let's call that the second marginal residual. In fact, this is, if you read some of the early papers, it's all written in this framework. And now you can get that the first marginal, which you'd really love to understand, can be written as a Vlasov system plus some correlation terms that are coming from the impact of the second marginal. And if you write this out, you can understand that this sort of second marginal residual is gradients convolved with this sort of stencil of the Green's function. And this is how you would write down now, if you believe that the correlation is driving, in some sense, the structure of this problem at this length scale. This is a PDE you could try and solve that would then import it. You would just need some information on the structure. How universal that is, I don't know. What would it depend upon? But there is a fair bit of data on that. It would be hard to gather this information from first principles. There's not a lot of tools, but it is a good topic for a machine learning sort of effort, I guess I would say. But this is sort of the basis of a continuum system, which would then incorporate some of this sort of quote-unquote stochastic or correlation structure that seems to be so present in water, particularly if you think two-particle correlation would lead you to that. In our context, where we do it with a dipole, you get this sort of structure. Here's the velocity, and here is the angular velocity. So you can sort of view this. You could take this at steady state if you want to. In fact, just take the velocity be 0. We're in an electrode. There's not a lot of, the average velocity is not very big. You could just take rho to be constant, u to be 0, and you get sort of a forced wave equation for this dipole moment here. Okay, but forced in sense by this sort of stochastic two-marginal, if you can understand this. If you can generate information on this, and there is a fair bit of sort of computational and also in some contexts some physical data that you can get. This is not an unknowable quantity here. But again, this whole structure is predicated on assuming two-point interaction. And so the rest of my talk, well, how much time do I have? I lost track of time. I'm sorry? Oh, 20 minutes, okay. Probably, okay, if I go quick, I can go quick, and then I'll be done. So the first thing you want to do, if you want to think about three-body interaction models, if you think two-body is not the right beast, what could give me a poster child for the very simplest three-body interaction. So if I give you a bunch of particles, just positions, and I form their distances. All I want to know is distances. The classic is the two-body interaction, the distance. But a three-body, well, one thing you could do that's 3 and not 2 is to look at the variation in the distances of your near neighbors. So you say, I got a bunch of near neighbors, there's their distances. If they're nearby, right, this says, okay, if any one of them is far away, I don't care. L is some sort of reference distance. Any one of them is far away, just throw it away. If they're my near neighbors, I want them to be similar. That is kind of like hydrogen. I was thinking about this. I think, what would this look like? And then just yesterday, we were at the Getty Villa, the Paris style. If you've been to the villa, not the museum. By the way, if you like archaeological history, the museum at the Getty Villa is stunning. Some of the best late Bronze Age pieces, or not even that late, mid-Bronze Age pieces I've ever seen in my life. But here's exactly a tiling where they look like all equilateral triangles, but they're sort of glued together with different lengths. So locally, all of the structures are, so they're the same problem. And this is a copy of a villa from outside Herculeum. So okay, even 2-some thousand years ago, people were thinking about these three-body interactions and how would you glue? What would it look like if you have a variation on your neighbor? And you think, okay, they cheat that this one's not equilateral, some of them, but it's quite clever, very clever, really very clever. They really do look like equilateral until you study it very carefully. Okay, so that one that wouldn't necessarily be constant. But okay, this is something you can take gradients of. It's relatively straightforward. I'm going to go to a more complicated energy, which is a Voronoi energy, immediately. And my cells, I think my cells are an excellent sort of a proxy for understanding volume-centric energies, things that want to maximize their volume. And one thing that does this is my cells in polymer chemistry. And in fact, Frank Bates, that sort of started working on this, wanted to think about the structure of electrons in a conduction band, but thought, it's better to have a more observable material. And so he started thinking about sort of forming spherical micelles in a polymer application and then modeling them based upon their Voronoi diagram. And so basically, you put them in, you get a volume, and then what structure of the Voronoi diagram would you like to minimize, and what sort of structure will you get? And this is most of the rest of my talk, is sort of trying to understand how big do you need in order to get good data? What sort of data, what structures do these three-body interactions have? And a Voronoi diagram is very much a 3 and higher body interaction. I'll just say people have thought a lot about Voronoi diagrams in this context. There's some interesting papers that say glassy systems and their glass transitions. There's sort of the asphericity, which is take the Voronoi diagram, take its surface area divided by its volume, subtract off 1. This is sort of how far you are from being a sphere. This sort of has a universal structure near this glass transition, that it really is not a silly quantity to think about when you're looking at these sorts of packing systems. In some sense, water is trying to pack. There is, and I would say, and this is my Axel slide. There is a very strong. So this found, and maybe I'm ahead of myself. The packing that they found was aperiodic. The optimal packing they found here, and this is a straight gradient flow. No, not a Hamiltonian flow, just going down the other. They found aperiodic packings, and this did not sit well with the community, and there was a strong effort to find, okay, no, these are really got maybe 2 types of volumes, but there are periodic packings, and so minimizing these sort of systems from self-consistent mean field theory, which is basically the DFT of polymer chemistry. You can find periodic structures which may have lower energy, so it could be periodic. But again, there's a huge resistance to saying something's just hardwired in. No, I am going to. And so my point is, okay, maybe these have lower energy, but the point I'm going to try and get to is they may also not be accessible at all. And there's a question of accessibility. And so Frank Bates, that's a reasonable representation of him. He said, let's do a model system. Let's look at star polymers where you have a core and all the arms radiate out. So now you can exchange that this is a fixed mass system. And when they're dry, it's like a powder. You put them in a confined box. You throw in some solvent, and they swell, and they form beautiful sort of Voronoi diagram, Voronoi structure. Some are clear, some are yellow, some are white, some are blue. So you can realize it's very good. It's calling that a Voronoi structure is not a huge guy. So I'm just going to put down the simplest Voronoi model you could think for this. I'm going to go to 2D. I'm just going to say I've got a polymer. It's got an arm. It looks at the boundary of its Voronoi diagram, and that arm length wants to be an equilibrium length, and it's a Hooke's law for the energy. And now let's just minimize these. Let's just run these guys down, run these sites down, do a gradient flow on this energy, and see what sort of structures you get as you go down the gradient. So maybe I'll sort of, some of this is really amazingly interesting, but also simple. As an average radius, it comes out very naturally. Just you integrate around the average distance to your boundary. You just average it. This is what drives it. If you take your energy, add them all up, expand out the quadratic, Ri squared d theta. Took us a long time. That's polar coordinate. We're teaching Calc 2. That's the area. That's the area of the cell. So these guys all this term and this term, they all average up. So all you have to minimize the energy, you want to maximize your total average radius of all these guys. They just want to be, they want as much space as they can get. And the point is that this is going to be very, very frustrating. Just totally for fun, if you're a mathematician, totally for fun, there's a reverse isoparametric inequality. If I give you a convex domain, its area is bounded below by pi r bar squared, where r bar is the average radius at any point inside the domain, right? The average radius of a point to its boundary. And there's a proof of this isoparametric is typically kind of hard. It's trivial. It's Jensen's. It's exactly Jensen's inequality. Just kind of cute. Okay, yeah, that's just, if you're a mathematician, there's something fun. There are a lot of ordered states in this system. If you give me a periodic domain, and I'm going to be interested in the number of particles, the aspect ratio of the domain, and the impact of this on the energy, all right? So if you just take a line through this guy, and the line repeats, and the line becomes periodic. Like there's a torus, if the line closes, put n dots on it, form a Voronoi diagram, that all the Voronoi cells will be identical. And because there's only a finite number of these, by symmetry, this cannot flow because you'd have to break symmetry. And so this has to be in equilibrium. So anything of this form, there's a finite number, but it's order of n squared. So there's a lot of ordered structure in here. But my point will be that you're never going to find it, right? And so why is this a three-body interaction if you haven't thought about Voronoi diagrams much? If you give you the points, these vertices are equidistant to three near neighbors. So you need 3 points to define a vertex, but you also need to know who's a near neighbor. So taking the 3 points to define the vertex is clearly a three-body interaction. Deciding who is your near neighbor is actually much more than a three-body. And the dominant bifurcation is taking Voronoi regions of one number of edges and then forming a 4-coordinated region and then breaking it, and then you can add and subtract one. And these are this will give you sort of these heptapenta defects, 5 and 7-sided, very naturally appear. And because of the Euler characteristic in the plane, you get every 5 has to have a 7, unless for some reason you form 6s and 4s or 4s and 8s, which are very rare. Okay, so you've got a lot of structure here, but you do have this sort of coordination number changing bifurcation. And these defects are sort of important. A brief word, the hexagon, you say, is there a global minimum? There absolutely is. When you can tile a periodic domain of aspect ratio alpha with endpoints, which is not always, then the hexagon is going to be the lowest energy. And the proof is sort of beautifully simple. Just drop normals. Here's your Voronoi diagram. Drop normals, cut them up into right triangles. So imagine you have a bunch of jigsaw puzzle pieces on your table. Each one is a right triangle formed from a Voronoi diagram. And then all you say is, well, I got all these right triangles. How many can I have? I can't have more than 12n because of Euler's formula. The angles should all sum up to 2 pi n, these interior angles. And the area, so give me my real thing. That's all. I don't ask that they can be put back together. And then you say, what minimizes this, subject to these two constraints, minimizes my energy, is the hexagon. And so if the hexagon exists, it's the global minimum. And so you could ask, when is the hexagon existing? That's a number theory question. Here's your aspect ratio of your domain. Here's the number of points. If there's a dot there, you can tile it with a hexagon. Very, very interesting. A lot of number theory sort of structure pulls into here. And these dots are all the energy of all the ordered structures. These ones I formed, these what I call single string, as I vary the aspect ratio. And you can see here's 1, 2, 3, 4, 5, 6, where I get exactly, these are where you get hexagonal. But you have a wide variation of energy. So just to normalize things, we defined a average excess energy, this E bar, which is the energy per particle per cell minus the hexagonal energy. So that has to be positive. You can't do better than hexagon. It may not exist, but if it exists, it's the best. You can't do better. So that should always be positive. Okay, so just to give you a rough idea, I think it's very helpful to see the gradient flow, because this really sort of mesmerized me when I first saw it. This is where I realized, so this is exactly, I'll take this one. This is exactly what this is a gradient flow of this. Okay, and there's the end state, but let's see if I start. So color is size. And the interior signal is 5, symbol is 5 or 7 or 8. And this is a flow. And I just want to convince you that we're really computing this down to equilibrium. So this is exactly what I thought would happen. That is exactly my intuition, and that is exactly exceptional. That almost never happens. In fact, what happens almost all the time, I don't know, I'll grab this one, is something more like this. This is just 400 or 200 particles, I can't remember. All right, you go down, and we're computing, and this is your energy above minimum, and you think, okay, that's going to relax, and no, it's a tremendously, I think, because of the 3-particle and higher interaction, 3-body interaction, this is a tremendously glassy, frustrated system. You just don't see this. I'm not used to seeing this in 2-particle interactions, not to this thing. So that's my, more or less, the moral of my story is, if you want to look at frustration in these systems and you think there is multi-particle interaction, it's really not the same to say, well, I'll approximate it by 2-particle interaction. That's sort of my game. Okay, so just to give you an idea, are these really equilibrium? That's the question I get all the time. Here's one of what we compute as equilibrium. What do? We compute the residual in our flow. We divide it by the smallest non-zero eigenvalue in the Hessian. The Hessian better be positive, or you're not on a minimum. There's 2 eigenvalues from translation, the non-zero. So you divide this by the Hessian. If that's smaller than a threshold, we stop. This is very exigent, and there is one step to making this a theorem. You need a bound on the 3rd derivative of the energy. If the energy is uniformly bounded, then as long as delta equilibrium is small enough, you are provably close to an equilibrium. So I'm very confident these are equilibrium. If you perturb them and come back, they come back to where they are. You can perturb this one I showed you, perturb it up to 10 to the minus 1, it comes back, and then too big, and it wanders off. So I'm quite comfortable that these are equilibrium that we're computing. This was a lot of computation, months on a cluster. It's 2D, not who cares? But yeah, it was complicated. It was a lot. So what we did, we formed a lot of bins of 400 particles, aspect ratio 1, 250 distinct simulations. And so here's a distribution of the energies as excess energy. And here's the number of defects you found, non-6-sided Voronoi regions. And it's a pretty good linear fit. It doesn't extrapolate down to 0. If you have no defects, you still have some residual energy in there, but there's a nice slope. And the slope, I think, I'll get on the next slide, but also a good spread. And so this is a 3-body and higher. This is some of these outliers, these ones here that I circled. Low energy, 2 here, and there's very high energy. So sort of just to give you some idea of what these look like. And this is the sort of states you might cycle through. Now, remember, initially, we want to do a Hamiltonian system. This is a gradient flow. So these are the low energy things you're going to circle around. Right? This is like trying to precondition your initial data. If I just went downhill on my data, how would I get to a low energy state? Well, even that is tricky. So just to be the n, this is my number of defects, and this is the oscillation, the number of defects. It sort of seems to converge. The number of defects tends to be about 8%. In these large. This is for alpha equals 1. So you sort of go to a sort of, there is a universal defect state, 8.8%. If you look at large n limit, so this is n up to 400 particles, I'll go a bit larger. This is this sort of ground state energy. This is what if I extrapolate linearly back, what would the 0 defect energy look like from this linear extrapolation? This is the energy I get when I calculate it. This other curve is what I call the frustration. That's my ground, that's my defect-free energy. This is so the frustration seems to grow, but to saturate, it doesn't seem. My intuition was large n, I would see hexagons. That's what everyone told me. Why are you computing this? Large n, you're just going to get hexagons. No, we don't. At large n, we converge to a delta function distribution in the energy. So this is n is 400, this is n is 1,000, and this is n is 2,000. The different curves are the different aspect ratios of the box we're computing on, 1, 0.5, 0.43. This dotted curve is the alpha equals 1 curve over here with the 2,000 particles, and then rescaled by this sort of self-similar structure. So there's this rescaled of the best estimate I have of the probability distribution for the energy. Right? This is energy. This is energy, and this is probability. This is the likelihood of seeing it. So this is the energy 1 to 6, same scale all the way across. And you see, as we get out to 2,000 particles in this simple problem on this 2D, the boundary conditions, which is the aspect ratio, starts to disappear around 2,000, but not even at 1,000 particles. So if you're thinking of multi-body interaction, how big do I have to be before my boundary conditions don't matter anymore? Big. Those are computational numbers. These were long simulations because our stopping criteria was so exigent. Okay, so the conjecture is that as n goes to infinity, you get a square root of n in 2D convergence to a limiting probability distribution for the energy, and it's some finite gap above the ground state, even though there is, like, what is that size? What is that number? Why is it converging? Okay, that's sort of that is what I think about when I'm thinking about multi-body interaction in these sort of models. It seems to be intrinsically more frustratable than a two-body interaction. And just to make my point a little bit more strong, what if I imagined a model, some molecular model with a combination of 2 and 3-body interactions, and if I could scale it right? In my problem, I had completely different time scales in front of different terms. Some terms scaled one way, some terms were multiplied by L squared, where L is the length of my dipole, very clearly a small parameter. Take the mean field limit, well, the two-particle interaction will give you something like this, and the 3-particle interaction, 3-by, will give you a cubic sort of convolution term. But from my point of view as a PD person, that's not fundamentally different. In the mean field limit, 2 and 3-particle interactions aren't fundamentally different. That if there's really a structural difference between 2 and 3-particle interaction, it's occurring at a level above the mean field limit. That's my intuition. Could be terrible, caveat, but that's what I think about when I'm thinking about this from a mathematical point of view. What is the minimum model I would need to understand this song of water? It probably needs 3-body interaction, and it's probably not in a mean field limit. That's my conclusion. Thank you very much.